All right, so let's look at these unit cell problems, okay? A little bit of math here. Now, at face value, the unit cells can be relatively daunting, but in complete actuality, they're really not that complicated. It may help you if you um, kind of draw them out, okay, just to kind of um to help you visualize what's going on here. But I think you'll see this and you'll go, oh, okay, that's not that bad. So in the first problem, it says determine the net number of sodium and chlorine ions in a unit cell of sodium chloride. So we're looking at salt, and let me grab my pen here. And they've given us this picture of salt. Now, hopefully, you've realized this is face-centered cubic right off the bat, right? So I know that because in my cube, right in the middle, I have this ginormous um, half um, of an atom, right? It's right in the middle of that face. So basically, all I need to do is figure out the different locations within the unit cell, all right, where an ion is, and I need to determine the fraction of the ion that lies within the boundaries of the lattice, within the boundaries of our unit cell. Okay, so let's do that. So sodium here, um, it's the little gray dot, right? So this little fella. So on each edge, there is a fourth, 1/4 of the um, of the ion. Now, how do I know that? Well, let's just look at this guy right here, right there he is. How do I know that that's a fourth? Well, if I wanted to complete this ion, right, I would need this cube, the next one, right, coming out. That would give me the bottom half. I would need this cube going up to give me the top part. And then I would need to finish it with this cube, right here, to get the whole thing. So there's a fourth in each cube. So again, this is face centered. I know that each of these is a fourth of an ion. So Na plus, I have 1/4 per edge. All right. And so I just need to know how many edges there are. Now, on a cube, there are 12 edges. Okay, that's just basic understanding of a three-dimensional cube. And so 1/4 of 12 is 3. Pretty straightforward. Now, there is also, okay, one of these in the very center of the molecule. So behind this guy and this guy and this guy, there is going to be one right there in the middle. And so I've got one per center, right? And there is one center, obviously. So that's one. So 3 and 1, there are 4 Na plus in my unit cell. Now let's do the same thing for Cl minus. Cl minus is my great big gigantic um, gray, no, not gray, wow, green things here. So let me get rid of some of this stuff. There we go. All right, now there is no chlorine in the very center, but I do have them in the faces and in the corners. So I'm still going to have to add two things together. So let's start with the corners. How many corners does a cube have? Well, 8. And in each one of these, there is an eighth of a chlorine because I would need one on all the way around. I'd have to get a total of an eighth there to fill that out. So I'm going to go 1/8 of my per corner, and that's also defined in your textbook. And there are 8 corners. Well, that's easy. An eighth of an 8 is 1. And so then I also have a half per face because it is face centered. And if I drew out right the next unit cell, I would get the other half of this guy right there. There would be his other half, right? So I have a half per face, and there are 6 faces on a cube, 6 sides. So that's 3. Okay, so I have 4 chlorine minuses. So the net number of sodium and chlorine ions in the salt unit cell is 4 sodiums and 4 chlorines. Now, does this make sense? Well, yeah, absolutely it makes sense because the formula is NaCl, and we do the formula weight, which, because it's an ionic solid, is based on the unit cell. It's 1 and 1, so it should be a 1-to-1 ratio. And so there we go. So we have 4 ions of each in our problem. Now let's take this and do one of the second problem, right? The more complicated one, the density. So it says the arrangement of ions in crystals of lithium fluoride is exactly the same as sodium chloride. Okay, so let's just stop right there. We know that we have a 1-to-1 ratio of lithium to fluorine. We know it's exactly the same as NaCl. So we know that there are 4 of each of these ions. And we know it's face-centered. It's a face-centered lattice, right? Or a face-centered unit cell. It says the unit cell of LiF is 4.02 angstroms on a side. What is the density of LiF? Okay, so density is always in grams per centimeter cubed, right? That's what we do, grams per milliliter. And we don't have grams and we don't have milliliters here. So you're thinking like, oh, all right, well, no big deal. If you don't have grams and centimeters, you must be able to find grams and centimeters. We're going to do a conversion. It gives us a length, angstroms, all right? And we can convert angstroms to centimeters at 10 to the negative eighth, right? Isn't that what I wrote down? Let me check my math. Yep, 10 to the negative eighth. Okay, so I can definitely convert angstroms to centimeters. Getting grams, not going to be that difficult, right? We know that the values on the periodic table are in atomic mass units, and we know that we can convert those over to grams pretty simply using 6.02 times 10 to the 23rd AMU is equal to a gram. So let's do our math problem. We'll start with figuring out how many lithium fluoride formula units are in our unit cell. So we know that we have 4 of each ions present because it's exact same as sodium chloride. So if you want to know how we do that, go back and watch the previous video. It's the same fractions, the same corners, the same edges, all that good stuff, because it's still a face-centered lattice. So I know that I have 4 lithiums. Now, on the periodic table, lithium is 6.94 AMU. And I need to use AMU because I'm talking about individual atoms here. These are atomic mass units, all right? And I'm going to add that to the 4 fluorines, which are right at 19.0 AMU. And that's going to tell me I have 103.8 AMU in my unit cell. So this is going to be in the unit cell. So there's the mass. All right, there's my mass. For volume, all right, well, volume's pretty simple, but we can visualize it, right? It says that the length of an edge is 4.02 angstroms. Well, it's a cube, so that means this is also 4.02 angstroms, and the height is 4.02 angstroms. So the volume is just, right, length times width times height. So that's going to be 4.02 angstroms cubed. There we go. So I have 103.8 AMU over 4.02 angstroms cubed. And if I wanted AMU per angstroms, that would give me a density right there. But I don't. I want to convert that. So let's convert our AMU first. 6.02 times 10 to the 23rd AMU. It's a conversion from year 1 chemistry when we talked about finding average atomic mass, and when we learned about the periodic table, that's the conversion to a gram. And then we also need to get rid of angstroms. 1 angstrom is equal to 10 to the negative 8th centimeters. And there we go. When we run our math problem, we do those things in our calculator, you will get 2.65 grams per centimeter cubed. There we go. All right, that's how we do the density problems for the unit cell. So you figure out how many ions are in each unit cell. You multiply by their atomic mass unit. You get an AMU value for mass. You take the length of the side of the unit cell. You cube it because it is a cube, right? So it's got a standardized volume there. And then you just convert. You need to know that 6.02 times 10 to the 23rd AMUs converts you to a gram, and you probably need to know that 1 angstrom is 10 to the negative 8 centimeters, right? If you know those two conversions, you'll be good, all right? If you have questions, let me know, and I'll be glad to give you guys a hand.